Filter difference, small but finite. Physics by example. Two small balls having the same mass and charge and located on the same vertical at heights h1 and h2 are thrown in the same direction along the horizontal at the same velocity v. The first ball touches the ground at a distance L from the initial vertical. At what height h2 will the second ball be at this instant? The air drag and the effect of the charges induced on the ground should be neglected. This is a problem from which we can learn almost everything about center of mass. Let us first visualize and picture the problem. Two small balls having charges, say for example, we'll suppose the mass is m, charge is q or plus q to be more precise, and another one same m and same charge, and these two are located at distances h1 and h2 along the vertical. Let this be the ground, and this height, for example, is h2, and height of that, let us say, is h1. And according to the question, the balls are given speeds in this direction. This is v, this is v. Now, what the question says is, the first ball touches the ground at a distance L from the initial vertical. That means after some time, the first ball touches the ground at L from the, this is, let me say, this is O, L from here, one ball touches the ground. Which could be that ball? That ball could be, should be this, ball 1, ball 2. So when this ball touches the ground here, where is the second ball? That's a question. We know very well, if one body like this is projected under gravity in a horizontal direction like this, it just follows a parabolic path and falls on the ground. Here, the only force acting on the ball is its weight. Of course, here also we need to ignore the air resistance. And we could write the parabola equation for that. But now, we cannot guess the path of the individual balls easily. The reason is that apart from mg of the mg of each ball, there is an electrostatic repulsion between the two balls. So apart from mg, there is a q by r square comes from Coulomb's law. So that force is also there on each ball. So just predicting the motion of the ball like this is not going to be easy. But that's where the center of mass idea helps. Let us see. When I consider these two balls as one system, whatever electric force they apply to repel each other will become the internal force. This is the system. So these two forces become internal, and weight of this will become external. This is mg, this is mg. So the total F external on the ball will be mg plus mg, which is 2mg in the downward direction. Now, the center of mass of this will behave as if this total 2mg were acting only on it. That is the basic definition of center of mass. That is F external vector. This is of course in general MACM. So a point which is representative of the whole system, which behaves as if the total external force are acting only on it, is defined as center of mass. Here 2 mg is equal to total mass is 2m ACM. This 2m going, we get ACM equals G. Look, each particle in the absence of the electric force would have gone with G, but now since there is electric repulsion also, it cannot go with G, but there is a point called center of mass which is going with G. So center of mass would follow a parabolic path is what we can guess, but to show the path of the center of mass, which is a parabola, we should know where is the center of mass. There comes the position of the center of mass. Of course, we need to take one origin to find out the position of center of mass. If I take this O as the origin along the, say for example, the y direction, this being x and that being y, I can write YCM equals MH1 plus MH2 by M plus M. So this turns out to be H1 plus H2 by 2. That means the center of mass is somewhere here in the middle of these two particles. So that mass of that we can think is 2m. So center of mass is a point which behaves as if the total mass were there at that point. So the 2m is in the middle of these two particles, that is at a height of h1 plus h2 by 2. This height is now h1 plus h2 by 2. The space is not enough. I'll rub this off. This is taken out. So the height from here, I'll extend this, is h1 plus h2 by 2. So center of mass is at a height of h1 plus h2 by 2 and its mass is 2m. And its acceleration we found is g, the acceleration to gravity. Now, the third one, the velocity of center of mass. This side I'll write VCM equals mv in the horizontal direction plus mv in the horizontal direction by m plus m. That is v again along the horizontal. Look, this mass 2m is going with v and has an acceleration g. Therefore, it is very easy to predict the motion of this center of mass, which will be of course a parabola. So this parabola will be like that. For example, this is the path followed by the center of mass. Center of mass actually is like a point mass. F equals MACM applies for that. Fx equals ma. Newton's second law applies for that. And that's the reason why we can always predict the path. That will be all the time it is a simple path. It could be a straight line, it could be a curvilinear path, but we can always make a guess of that path. Now here we couldn't actually know the individual path of the particles because there are two forces, mg and kq and q2 by r square. The acceleration is not g, but the center of mass has an acceleration g and a mass 2m. The total external force 2mg is acting only on it. Now, our job is to find out where is this particle 2 when the particle 1 is here. So since center of mass has to be in between these two particles, it's not difficult to guess that this particle, second particle, is somewhere here in the y direction. Of course, to say that this is in y direction somewhere here, there is something we need to note here. The problem is cleverly framed. The velocities were given same. and masses are same. That is, of course, masses need not have to be same. Velocities are same. That means due to that internal force, repulsive force, which is acting along the line joining them in the y direction, that's not going to change the velocity in the horizontal direction. I hope you followed this. Though the external force is there, this V will remain constant only, because both this KQ1 Q2 by R square electrostatic force and mg are in vertical direction only. So in the horizontal direction, since the speeds are not going to change, the balls are not going to get separated in that direction. There won't be a relative velocity between the balls in the x direction. Therefore, definitely we can make a guess that this second particle is going to be in the y direction only. Now, when this particle is here, where is our center of mass? The center of mass is somewhere here. How much distance it had fallen down, we need to calculate. That is, say for example, y. Y equals, we know, half g t square. And that y equals half gt square when we write, we are not taking the initial velocity of the center of mass in the vertical direction. Naturally, because the whole velocity is in horizontal direction, there is no velocity in the downward direction. But how much will be this t? That t will be L by V. Why? When the first particle touches this ground here at a distance L from O, horizontal velocity was remaining same. There was no acceleration in that direction. Therefore, simply this L by V gives you the time. Now this is y. But our job is not yet over. We need to find out where is this particle. For that, I should find out my center of mass from the ground. Where is that from the ground? I will find out. So that ycm equals, it was at h1 plus h2 by 2 first, and it had fallen through half gt square. So h1 plus h2 by 2 minus half g t square is the positional center of mass after this time. Since ycm is known now, I can guess the position of the second mass. Now if I write the ycm now after time t, it is m into 0 for one particle which is already at the ground, plus m into some y1. This y1 is the position of the second particle. So by 2m. When I did that, I'll get y1 equals simply 2ycm. Is it right? Yeah, my1 by 2m. y1 by 2 is ycm, so y1 equals 2ycm. Therefore, it becomes 2 into h1 plus h2 by 2 minus half g into L by V whole square. So this turns out to be h1 plus h2 minus the 2 cancelling again, g L by V whole square. This is where our second particle will be when the first particle touches the ground at the distance shown. So with this one problem, we've learned so much. We can see first the definition of center of mass. The basic definition of center of mass is that it represents the whole system. Center of mass of a system of particles is a point which behaves as if the total external force were acting only on it. That's one thing. Second, the position of center of mass. It is the weighted average distance of the particles from the origin. That is, in this case, we wrote it in y direction, m1 y1 plus m2 y2 by m plus m1 plus m2. And then velocity of center of mass. It also will be a similar formula, m1 v1 plus m2 v2 by m1 plus m2. And apart from all these things, the usefulness of center of mass idea, especially when it is difficult to guess the motion of individual particles of the system, and if it is, and it is easy to discuss the center of mass motion. Once you know the center of mass motion, you can predict the motion of the other particles from the center of mass.